I'm going to discuss how we derive the result for energy flow in electromagnetic fields that is sometimes known as Poynting's theorem. So let's start by thinking about the total energy in an electromagnetic field, and we know that we can write EM is the volume integral of a half d dot E plus a half b dot h dv. We frequently then use a useful result. U, the energy density in the fields, is a half into d dot E plus b dot h, but you should note that there is a little bit of controversy over the whole question of where energy is stored. The total integral is perfectly reliable. Sometimes there are debates over exactly how we distribute things, but we're going to use that energy density because it's a very helpful and useful result, and it is at least perfectly reasonable. So let's consider a situation where we've got a set of fields and charges and currents. The charges are going to be potentially moving. The currents can potentially change with time, though remember, of course, that a current is just a moving charge. And since charges are moving, work will be done. And so the question is, what is the relationship? What is the relation between the work done the energy stored, because as work is done, energy will be stored or released, and here's the key point, energy flow. Because if work is being done, then potentially energy will also flow. So we're going to consider that question. Let's start by thinking about the work done on a single charge by a set of fields. So we're going to have a single charge Q with velocity, let's say v, and we're thinking about the work done over a time interval dt. Now, during that time interval, the charge will move by a small distance, dl, which is just the velocity dt. And we know perfectly well that the work done by a force in moving over, the work done by a force over a distance can be written as dw is equal to the force dotted with dl, which of course is then just equal to f dot v dt. Now, since we have a charge which is moving in fields, we can write the following. You say that dw is equal to q into E plus v cross b, that's just the electromagnetic force, dotted with v dt. And since v dotted with v cross b is 0, we can write that as equal to q E dot v dt. That's for a single charge. Now let's consider a charge density. And as usual, we will notate the charge density as rho. Here we're going to turn that single point into an integral. So dw in this case is the volume integral of q E dot v dt. I'll put brackets around that to indicate that that's the integrand, and then we are integrating with respect to volume dv. And therefore the instantaneous power on this collection of charges, sorry, that shouldn't be a q there, that should of course be the rho. The instantaneous power we write as dw by dt, which is just the volume integral of rho E dot v dv, but we know that rho times v, the velocity, is equal to the current density, so dw by dt, the instantaneous power, is given by the volume integral of E dotted with j dv. So that's got us to a useful point. What we want to do now is to rewrite that in terms of fields, purely in terms of fields, because we're thinking about the energy stored in the fields. And how are we going to do that? Well, we're going to use some of Maxwell's equations, obviously. And we'll start with the Ampere-Maxwell equation, which is the equation that contains the current density J. So we're going to say that that's equal to curl of H is equal to J plus dd by dt. And therefore we can write the term E dot J, we'll come back and integrate at the end, is going to be equal to E dotted with curl of H minus dd by dt, which is written like this: E dot curl H minus E dot dd by dt. Now if we just stop and look at that for a moment, you might notice that this term here on the right, E dot dd by dt, looks something like the time derivative of an energy density that we showed above, and that's reassuring. The first term is perhaps a little bit more awkward, and we need to think about how to get rid of it. So what we're going to do is we're going to start by thinking about a trigonometric, well, a vector differential identity. The divergence of a cross product is given by the following. So if you've got the divergence of E cross H, that's equal to H dotted with curl of E minus E dotted with the curl of H. And of course we know that we can replace curl of E with minus dB by dt. That's quite appealing, replacing the curl of E with minus dB by dt, because that gives us a term of H dot dB by dt. We've got a term of E dot dd by dt, and we're starting to see a symmetry and a completeness that would be rather useful. So let's just go back and rewrite that. We find that we have E dotted with the curl of H is equal to minus H dot dB by dt minus the divergence of E cross H. And we're going to be okay with that, so that final term on the right may look a little bit awkward, but it's involving the fields crossed together. We're not taking any curls, and therefore things are moving a little bit in the right direction. So let's return to E dot J. We find that we have E dot J is now given by minus the divergence of E crossed with H minus H dotted with dB by dt minus D dotted with dE by dt. Now, where do we go from here? How do we deal with those those derivatives of energy densities? How do we change those? So if we're in a linear isotropic homogeneous material, then we can write D is equal to epsilon R epsilon naught E, and therefore we can do the following. We can say that D by dt of epsilon naught epsilon R E dotted with E, and of course that is just D by dt of D dotted with E, is equal to epsilon naught epsilon R dE by dt dot E plus epsilon naught epsilon R E dotted with dE by dt. And that is just twice D dotted with dE by dt, and therefore D dot dE by dt is just a half D by dt of D dot E. Or if you prefer, we can say it's D by dt of a half D dot E. In other words, that's the time derivative of the energy density. You can do the exact same thing for the magnetic terms, and so what we have now is that E dot J is equal to minus the divergence of E cross H minus D by dt of a half D dot E plus B dot H. And what we want to do now is we want to return to the integral that we had above. So we can say that total work done, dw by dt, which is the volume integral of E dot j dv, is equal to minus the volume integral of div E cross h dv, and we will come back to that term in just a moment, minus d by dt of the volume integral of a half, sorry, let me rewrite that, volume integral of a half d dot E plus b dot h dv. And so again we can say that the volume integral of E dot j dv is equal to minus, now I'm going to use the divergence theorem and convert the volume integral of a div into the closed surface integral of the quantity that was inside the div, that's E cross h dot ds, minus d by dt of the volume integral of u, the energy density. So now we have the following. We have the work done by the fields. We have the change with time of the energy stored in the fields. And we have this term here on the left, the surface integral, the closed surface integral of E cross h dot ds. And what we're going to do is we're going to follow Poynting in identifying that integral as the outward flow. Of energy through the surface. We frequently define the quantity E cross H as follows. I'm going to write it as N. You will often also see it written as S. This is known as Poynting's vector, or possibly just the Poynting vector. You'll see both. And it is often identified with the energy per unit time flowing through per unit area. Though it's important to note that really we can only actually identify the closed surface integral of the Poynting vector with the energy flow. Anything else risks misinterpretation, but it is often done that way. And the equation up here, which I'm just going to highlight in red, is known as Poynting's theorem. And it is an identification of the different terms in the energy flow. Let's just briefly consider one thing. If we set dw by dt equal to 0, in other words, there's no work being done, then what we would find is the following. We would have that d by dt of the volume integral of u dv, so that's the time change with time of the energy stored in the fields, is equal to minus the closed surface integral of the Poynting vector dot ds. So if the energy flows outwards, then we lose energy stored in the fields and vice versa. And we can rearrange that, and we can just do that as a volume integral of du by dt plus div dot n dv is equal to 0. And that looks very, very similar to the continuity equation, and it only applies in this case when dw by dt is equal to 0. But again, it's very interesting to note that you get these things of a scalar taken with a time derivative added to the divergence of a vector, and this will come back when we think about special relativity and electromagnetism. So Poynting's theorem and the Poynting vector are extremely useful quantities. They allow us to think about how energy flows. They allow us to do a number of very valuable and powerful calculations. You should remember that the physical significance is always related to the total volume integral.